I am going to talk a little bit about big science on PRP, big with a capital B. This is collaborations that are fundamentally global, anything from hundreds to thousands of collaborators. And I'm going to organize this around the central message that what these organizations benefit from PRP is its versatility. In other words, I'm listing 3 types of ways that people use it. Either PRP as a production infrastructure to do their science, and this is enabled via PRP as an OSG site, and I'll explain what that means. And that's how IceCube, LIGO, and Nova use the GPUs on PRP. You saw this in the very first presentation by Larry Smarr. The big bulb of large-scale use was IceCube using GPUs this way. A second type of use is PRP for interactive machine learning to develop new algorithms, et cetera, et cetera. Basically, just like all the other machine learners, there are lots of machine learners inside these collaborations, and they've discovered PRP and are using it for their home use. And I give you examples from one such person. And then the last one is PRP is also used for cyber infrastructure R&D because it's an unusual platform given its global distribution, where you can easily test anything on any RTT that you could want, almost, meaning a wide range of RTTs. So let me dive in. First one is the production use. IceCube used up to 15,000 GPU hours per day on PRP and about 1 million hours total in 2 years. And that was shown on already by Larry. PRP is integrated into OSG as a standard batch resource, and it allows IceCube, LIGO, Nova to use PRP in backfill modes. In other words, to consume the leftover GPU, so to speak, that the machine learners, when they leave behind from their interactive work. And this becomes an integral part of their global production infrastructure, meaning to people in IceCube, LIGO, Nova, they don't even are aware that there is Kubernetes. They're not aware. They just know, they don't even know anything really about PRP. They just submit to OSG and magic happens, plumbing gets sorted, and voila, resources get consumed. So it's very transparent to their global operations. And an example of what is done with it is the IceCube collaboration. They have an instrument which is a cubic kilometer of ice at the South Pole. It's instrumented with about a little more than 5,000 optical sensors. It literally, you bore a hole into the ice. In other words, you melt it. You submerge a phototube or a string of phototubes, and the phototubes are then 1 kilometer deep in the ice, and 1 kilometer deep away from the surface, you then build a kilometer cube array of these phototubes. And to understand the universe by detecting galactic neutrinos is the objective. That's the science. However, in order to understand the detector, meaning this array, they have to understand the ice properties because they depend on both depth and wavelength. And I've shown you here a view graph of this. And the GPUs are used to propagate light through Arctic ice in simulations. And doing this is essential to improve the reconstruction and to understand the detector response model, so that when you see something, you actually know where to point back, so that you know where this neutrino came from in the universe. The second type of examples is all of these here. All of what you see on this slide is work done in Javier Duarte's lab at UCSD. And you see the different students who've worked on these various projects. He, in essence, he's a machine learner who uses machine learning for all kinds of different problems, ranging from reconstruction in real time in FPGAs, or for particle tracking in the detector, to anomaly detections, meaning did something break, did something go wrong, via another type of machine learning. There is graph-based physics data generation. The idea here is that you would accelerate simulations by building artificial intelligence into it. And down here, there is another reconstruction type algorithms that is based on machine learning. So Javi uses PRP interactively, both the FPGAs and the GPUs, for a large variety of projects with his students and collaborators. Then finally, I wanted to point out that the very fact that PRP has such a wide distribution, here I've shown you just a map of a few places that in PRP that we've used for an R&D project where we try to understand the throughput of grid FTP and HTTPS as a function of latency, as well as its stability. And that's this graph here from a publication. And there aren't any other places that I can easily think of other than the cloud to where you have this kind of easy to use, globally distributed servers that you can mess with and use for transfer testing at a global scale. And I think I'll leave it at that. I have a couple comments on the future, but let's go to the Q&A.
Well, Frank, thank you. We really don't have time at this point for Q&A, but I would encourage people to put any questions as we move forward in the Q&A box, and we can answer them offline. I'd like to thank our panelists. Gee, there's so much good work that's been done on the Pacific Research Platform. It's hard to encapsulate it, and you did a wonderful job.